In this video, we're going to be taking a look at 3 example problems that use the first law of thermodynamics. Now, the first question says a gas absorbs 900 joules of heat while it does 500 joules of work. If it has 100 joules of internal energy to start with, then what is its final amount of internal energy? So we have a gas taking in 900 joules of heat. And it does 500 joules of work, which means that the gas itself is losing 500 joules of energy by transferring it to the surroundings. Now, there's 2 versions of the first law of thermodynamics, which is delta U equals Q plus W, and delta U equals Q minus W. Q plus W means that you're focusing on the system, and Q minus W is focusing on the surroundings. So this one we're focusing on the system, so we're going to use delta U equals Q plus W. Now from there, we have delta U that we can break into final minus initial, so UF minus our initial, which we got in the beginning, which was 100 joules. And then in the problem, we got our other 2 values. You would just want to make sure you're careful about whether it's positive or negative, whether heat is being transferred to the system or to the surroundings. And then secondly, is the system doing the work or having work done on it? So we have a Q that we identified as 900 joules because the heat is being transferred to the gas. And then we have negative 500 joules because the gas is doing work on the surroundings. Now from there, just some basic algebra. 900 minus 500 is 400 joules, and then plus the 100 joules from the other side. And then our final answer is the final internal energy is 500 joules. Now for our second question, we have an isobaric situation, and isobaric meaning that the container and the gas remains at a constant pressure. So according to the question, we have a container that has a volume of 1 cubic meter to begin with, and then expands to 3 cubic meters as it gains 200 joules of heat. So we have 200 joules of heat being absorbed by the gas. And then we're looking for what is the change in internal energy. So again, we're going to use delta U equals Q plus W, and in addition to that, we're also going to use W equals negative P times delta V. Okay, now when you do focus on the system, you have plus W and negative P delta V. When you're focusing on the surroundings, you have negative W and no negative over here. Either way, working this out mathematically and conceptually is going to be very similar. So let's go ahead and take a look at what we got. We have a Q value of positive 200. We have some volume, so we can find our delta V, and we have a pressure of 1 atm that we need to convert. So we have 1 atmosphere, and then we're going to multiply that by 101,325 pascals, which obviously still equals 101,325. So that's going to be our pressure for both containers because it's an isobaric situation where the pressure remains constant. Now what we can do is a little bit of a substitution where we take negative P delta V, and then drop that in for the work. And then we can go ahead and find our delta W, our change in internal energy. So we got delta W equals, and then we have our 200 joules of heat that we got earlier in the problem right over here. And then since there's a minus here, I'm going to go ahead and put minus the product of the pressure that we just said is 101,325 pascals times our delta V. Remember, delta V is always final minus initial. So we have 3 minus 1. When we work that out, the product of these two comes out to 202,650. So we have 200 joules minus that fairly large number. And then we have a final change in internal energy of negative 202,450 joules. Now, the reason why the change in internal energy is negative, that means the system is transferring energy to the surroundings. Because if the volume is expanding from 1 to 3, it's applying a force over a distance and pushing outward on the surroundings, therefore losing some internal energy, which we see here as our final solution. All right, so let's go ahead and get into our final question. For this one, we have a container that releases 700 joules of heat. So I'm going to go ahead and put negative 700 because it's leaving the system. And then the volume condenses from 10 to 2. So I'm going to go ahead and make a smaller one over here. We have a volume of 10 and then a volume of 2. And then again, we're looking for the change in internal energy. So we're looking for delta U once again. So a couple things. We do have the constant pressure of 2 atmospheres for both of those. So let's do a little bit of converting before we plug some stuff into our formula. We have 2 atmospheres times our 101,325 pascals. And that will give us our pressure for the container before and after because it's isobaric. And then we also have some units that are in liters. We have 10 liters and 2 liters, which we can go ahead and convert into meters cubed. But actually, we'll wait and find the delta V later and then go ahead and convert that a little bit later in the problem. So we have our change in internal energy equal to our Q, negative 700, because heat is being released and not absorbed. And then again, we're going to make that substitution of putting in that negative P delta V. Okay, so that minus comes from the formula being W equals negative P delta V. All right, so we have negative 700. We have 202,650. And then for the delta V, we have 2 minus 10, final minus initial. 2 minus 10 is negative 8 liters. Now, in 1 liter, we have 0.001 cubic meters. So what that's going to do is basically make us slide our decimal a couple over, and then we have negative 0.008 meters cubes. So now we're in all of these standard units that we need for this problem. So we can take 202,650 times negative 0.008, which gives us negative 1,621.2 joules. So we have negative 700 minus 1621.2. So since we're subtracting a negative, that is adding this value in the end. So we have negative 700 plus 1621.2, which gives us positive 921.2 joules in the very end for our delta U. So when you set these problems up, what you want to do is make sure you do some basic diagramming just so you're clear on where your positives and negatives lie for your Q values and for sometimes for your work values as well, and getting a good visual of how the volume changes as far as if it's condensing or expanding is always a good reminder of what's happening conceptually, so that when you plug in your numbers, you want to make sure that the negatives kind of follow what's happening in the physical situation. And for this one, we ended up getting a positive delta U because the surroundings are applying a force over a distance and compressing that container down to 2 liters. Therefore, it has an increase in its internal energy. So I hope that was helpful to you in seeing those 3 examples. Thank you for watching and listening.